S-Chan presents Educational Video Lectures. Difficult concepts made easy. Study anywhere, anytime.
Welcome to S-Chan Academy, and I am Dr. Anmol Bhatia. We are learning the course Applied Thermodynamics, and in that we are studying the topic steam turbines and nozzles. So the steam turbine and nozzles is a critical concept that is used in case of power generation, and we'll be learning this concept through this video.
If you want to study this topic in detail, refer to the book by S-Chan Publishing. Link is provided in the description box.
So the topic, as I've told you, is steam nozzles and turbines, and straight away we are coming to the concept, but this concept lies somewhere around the physics of this movement of air, and in order to learn that, we need to understand equation of continuity first. So herein we need to consider a non-viscous liquid, and that would be a streamline flow is flowing in a streamline flow in a particular tube of varying cross section. So you have a particular tube and the cross section is varying. You can see that the different volumes are there, and area of cross sections are also different. You have this A1 cross section in the initial part and A2 area of cross section in the other part. So you can see that the volume of the water entering per second is area into the this part velocity. So this particular velocity is basically related to the velocity of flow of the liquid. And if I talk about this volume portion, so volume can be represented as area multiplied by the distance. If I divide it with time, I'll get this distance over time as velocity. So area into velocity is a particular part that is indicative of the volume of water which is entering per second. So the volume per time is area multiplied by this velocity part. The similar concept can be applied for the other section, which is the B section. So that would be A2 into V2. Now if I consider the mass at both the regions, which is the first region and the second region, so mass is particularly calculated by multiplying it with the density. So volume into density is particularly the mass, and if we assume that the mass of liquid is same, we are having the same liquid flowing inside the tube, then this these two terms particularly cancels out, and density is particularly uniform throughout this particular region. So ultimately we come across this equation, which is A1 V1 equals to A2 V2, or you can say that the product of area and velocity flowing is constant. That is particularly called as the equation of continuity. Now we have other set, which is, before learning this turbine, we have to understand the steam nozzle part also. So steam nozzle is basically an insulated passage of varying cross-sectional area through which the heat energy, and particularly that heat energy is enthalpy, the pressure of the steam is converted into the kinetic energy. That means we have to particularly use the motion of or the movement of that particular steam, and pressure is being built up, and we need to convert that into kinetic energy. Now what happens, we have certain functions of the nozzle. First thing, as I've told you, that it converts this heat energy into the kinetic energy, and another function is to direct the steam at high velocity into the blades at the required angle. So we particularly have certain blades in case of the turbine, and those blades would be aligned at certain angles. Now, what happens, this nozzle will direct that high velocity jet into the blades of the turbine at the particular angles. Now, what are the different applications? The first and foremost application is there in the steam or gas turbines, which is used to produce high velocity jets. And another application is there in the jet engines and rockets, and that particularly is used to produce thrust for a particular operation. And now we have different types of nozzles with us, and those categorization would include convergent nozzle, the divergent nozzle, and the mixture of the two, convergent divergent nozzles. So what we have, the first thing is convergent nozzle. So convergent nozzle is having the large entrance, and it appears as a taper, so it gradually tapers into a smaller section at the exit. So initially it has a wider opening, and when it basically tapers into a smaller section, so it has no diverging point. Then you have the case of divergent nozzles. Now, divergent nozzle is just opposite of the convergent nozzle. It is basically a nozzle with the small entrance, and it tapers gradually into the large section at the exit. So initially you can observe that it has a smaller cross section, and when it moves inside, it gradually opens into the larger section. So it has no converging point at the entry. This is particularly called as divergent nozzle. And if I talk about convergent divergent nozzle, so convergent divergent nozzle is that particular nozzle which is used widely in steam turbines. And this nozzle first converges into the smallest section, and from there it diverges into the larger section. So you understood what is the case. It basically tapers into the smaller section, and then afterwards it diverges basically into a larger section. So this smaller section of the nozzle is basically the minimal section is particularly called as the throat. So this particular section is called as a throat. So what happens here, this divergent portion of the nozzle allows higher expansion ratio, and it increases the pressure drop. So herein you can observe that pressure would increase, and ultimately this would lead to increase in pressure drop, or you can have a higher expansion ratio. So there are certain specifications of convergent divergent nozzles. So the taper for the diverging side of the nozzle, it ranges from 6 degree to 15 degree. And if the taper is above 15 degree, then the turbulence is increased, and if it is less than 6 degree, then the length of the nozzle will increase, right? So this is a particular guideline in case of the convergent divergent nozzle. Now let us have a discussion on Mach number. So it is particularly required when we are particularly observing the motion of any fluid, namely air. So it is basically the ratio of speed of the object moving through the fluid. That means when we are particularly moving inside the air, and there is a local speed of sound which would be there. So Mach number is the ratio of the speed of the object which is there inside the fluid and the speed of the sound. So herein, if the symbol represent, what does the symbol represents? M basically represents the Mach number. V is the velocity of the source which is relative to the medium, and V sound is the sound of speed of the sound in that particular medium. So it varies by the composition of the surrounding media and the local conditions, basically the pressure conditions or the temperature conditions. So it varies according to that. Now, as far as the flow is concerned, so we have certain categorization of the flow, like if the Mach number is less than 1, then the flow is called as subsonic. If it is equal to 1, then it is called as sonic flow. If it is greater than 1, we name it as a supersonic flow, and if it is greater than 5, we call it as a hypersonic flow. So Mach number is particularly one of the critical number that particularly defines the type of flow which is there. So if it is less than 1, it is subsonic or sonic or supersonic or hypersonic values. Now we'll have a short discussion on what is a turbine, and then we'll move ahead. So turbine is basically the prime mover in which the rotary motion is obtained by the centrifugal force. So the centrifugal forces are into picture in case of this turbine part, and that particularly is brought into the action by changing the direction of the jet. So when we switch or changes the direction of the jet, the fluid escapes from the nozzle at high velocity. So our particular estimation is whenever we insert the fluid inside the turbine, so it have that centrifugal force and it escapes at a high velocity. This is what we expect from a turbine, and if that particular moving fluid is steam, then it is specifically called as a steam turbine. Now, steam turbine has certain classifications on the basis of certain grounds. So let's say on the basis of action of steam, we have two categorization: impulse turbine and the reaction turbine. Then we have the classification based on the steam flow, which is the axial, nozzle or the radial or tangential type of flow. Then on the basis of number of pressure stages, we can have single stage, we can have multi-stage type of systems. Then on the basis of method of governing, we can have a throttle governing case, nozzle governing, or the bypass, or you can say that we can have the combination of throttle and the bypass case. So we'll be discussing some critical aspect of these two categories, which is impulse turbine and the reaction turbine, in the later part of the video. We stop here for a short break. After coming back from the break, we will learn the intricacies of impact turbine and the reaction turbine. Thank you.
Now quality learning is easily available at your doorstep. S. Chand Academy brings detailed lectures based on AICTE curriculum as per the New Education Policy 2020. So do not forget to subscribe to the S. Chand Academy and access the wide world of knowledge conveniently sitting at your home. Stay connected and keep watching S. Chand Academy. Happy learning!
Welcome back to S. Chand Academy after the break. Before going to the break, we have learned certain concepts of steam turbines. Additionally, we have learned the topic of nozzles and certain terms which are related to the same, such as Mach number that indicates the different types of flow. Now in this part of the video, we will be learning the intricacies of impulse turbine and reaction turbine. So straight away I am coming to the topic, and the topic is impulse turbine part. So impulse turbine is that particular type of steam turbine wherein the rotor derives the rotating force from the impact force. So basically we have to give an impact and then we start giving the impact, and from that particular part it derives the force or the direct push of the steam on the blade. So when the steam is impinged on the blade, then it gets that impact from that particular steam, and then it derives that particular rotational force. So it was first built up in 1883 by the Swedish engineer D. Lavelle, and the impulse turbine, it basically consists of a rotor which is mounted on a shaft that is free to rotate. So you have a rotor and that rotor is mounted on a shaft and that rotor is free to rotate. Now attached to that rotor there are set of curved blades. So on that rotor we particularly have those curved blades, and the nozzle particularly directs the high pressure and the high temperature steam towards the blade and the turbine. So basically what happens, the blade catches the impact force of the steam and rotates that particular component from the force which is derived from that steam. Let us have a diagrammatic presentation of the same. You can see that there is a shaft and this component is attached on the shaft, and you can see these blades which are fitted on the surface. So these blades are like this, and this is the particular portion that we want to rotate. Now you have jets. Now this one is a jet, this one is a jet, and when this you can say this impinges on the steam impinges on the surface. So what happens? These blades starts to rotate, and ultimately it will have that driving force that drives the entire turbine. So this is one of the concept which is particularly called as impulse turbine. So herein you can see that what happens particularly inside. So from this nozzle, I have labeled it 1, then 2, then 3. So it goes into the blade, and then from the blade it moves outside. The similar manner, the similar process you can see. And additionally, this 4 is the input that we are having, right? So the direction of the blade because of the force. So the 1 indicates that the steam first enters the impulse turbine through the fixed nozzle. So you have a fixed nozzle here, and the steam enters into the turbine through the fixed nozzle part. Now in the number 2, that indicate that steam strikes the blade that are free to rotate. So there are blades, certain blades, and those blades are free to rotate with the strong force which is enough to move those particular blades. Now 3 indicates that the steam exits the blade towards the condensing system. So there is a condensing system in which the steam condenses into water and it moves into that particular region. Right. Now number 4, the direction of the blades due to the force of the steam. So this 4 particularly indicates the direction of the blades due to which it indicates or it has a force on the particular steam. Now coming to the reaction turbine. So reaction turbine is that particular type of turbine which works on the principle of rotor spins. Now what is this rotor spin? As this name suggests, the reaction force is there rather than the impact or the impulse force. So you have a reaction force in terms of this reaction turbine. In case of impulse turbine, you had impact force. Now what is this reaction force? So you can see that there are no nozzles in the impulse turbine. So in impulse turbine, we had fixed nozzle, and that fixed nozzle was impacting the steam on the surface. But here we don't have any nozzles to direct that particular steam. Instead, the blade that project radially from the outer edge of the rotor are shaped and mounted so that the shape between the blades created by the cross section, it creates a particular shape of the nozzle. So we don't have a nozzle particularly, but the shape of the blade particularly when comes in contact with that particular steam ultimately becomes a nozzle, and then it directs the steam to guide on the surface. And then these blades are mounted on the revolving parts and thereby it allows it to rotate. Now in the reaction turbine, the fixed blades which are having the same shape as that of the moving blades. So you have 2 blades, one is the fixed blade, another is the moving blade, and you have the same shape, and they are mounted on the outer casing where the rotor revolves and set to guide the steam into the moving blade. We understand this with the help of this diagrammatic presentation. You can see that the shape of the blade, fixed blade and the moving blade are same, and herein we don't have the nozzle. The same aspect that we have studied in the impulse turbine, we have to study in this particular case also. You can see I have labeled it with 1, 2, 3 and 4 numbers. Number 1 basically indicates that the steam enters through the section of the curved blades in a fixed position. So these curved blades are there in a fixed position and the steam is entering into the surface, right? Now the steam then enters into the set of moving blades and creates enough reaction force to rotate them. So it moves into this particular space, and it particularly creates enough amount of reaction forces or the reactive forces so that these blades rotates, and ultimately steam exits the section of the rotating blade. So steam moves out of this section, and this 4 indicates the direction of rotation. So in this particular direction, this rotation is carried out. So the reaction turbine has basically 3 main forces that are acted on the surface. First is the reactive force that is being created on the moving blade. So we have a moving blade, and there is a reaction force being created on the surface, and it expands. It basically increases the velocity and moves through the nozzle, and we have that particular spaces wherein the steam moves inside those spaces and creates that particular motion. Second is the reactive force which is being produced on the moving blade as the steam passes through the changes direction. Steam passes and it basically changes the direction. So there is a reactive force which is there on the moving blades as well. And the third is to the lesser extent from the impact force of the steam of the blade that rotates the particular reaction turbine. So in totality, you have 3 forces which are acted on the surface. So this is example of impulse turbine. You can see that there are nozzles, and nozzle is particularly creating an impact on the surface so that this turbine rotates. And in case of the reaction turbine, you don't have nozzles, rather you have the same shaped fixed blades wherein the steam moves and it creates reaction force to rotate this particular turbine. So this particularly indicates that there is the steam pressure initially it drops and it becomes constant, and the steam velocity increases and then it decreases, and then finally it becomes constant. Wherein in case of reaction turbine, you have another aspect. You had constant pressure initially, then the pressure drops up to a certain stage. Herein this velocity part remains the same, wherein you can see that the velocity increases and then it decreases to a certain extent. So this is the particular case. So if I talk about the difference between the two, in impulse turbine there are nozzles which are placed in series, whereas in reaction turbine you don't have any nozzle, rather than you have the blades fitted on the surface. And in impulse turbine, the pressure falls in the nozzle, while in the reaction turbine, in the fixed blade, the boiler pressure falls. So both the categories, the same pressure drop is there. And in impulse turbine, the kinetic energy of the steam increases in the nozzle, while this work is done by the fixed blade in the reaction turbine. So same concept, you had nozzle, and nozzle increases the kinetic energy, whereas the fixed blade increases the kinetic energy. Now there is one term which is compounding of the impulse turbine and the reaction turbine. So compounding is done basically for the impulse turbine in order to increase the efficiency, whereas no compounding is necessary in case of the reaction turbine, because ultimately the efficiency is increased in this particular case. And in impulse turbine, there is a pressure drop per stage. The pressure drop per stage is more than in case of the reaction turbine. So if you look at that particular diagram, so there is pressure drop per stage, and there is this pressure drop per particular stage. So this particular pressure drop is there for the impulse turbine, and that value is there for the reaction turbine. So you can observe that point, that pressure drop per stage is more than in the reaction turbine. Additionally, not much power can be developed in impulse turbine, whereas reaction turbine develops more power. Efficiency in case of impulse turbine is lesser as compared to the reaction turbine, and impulse turbine require less space than the reaction turbine. Manufacturing of this impulse turbine blade is not difficult as that in the reaction turbine case is difficult, because in case of impulse turbine you have nozzles and you have the fixed blades, but the shape of the blade varies in case of the reaction turbine, and you don't have nozzle there, so you need to link it with the blade configurations. So with this, we come to the end of the video, wherein we learnt about the intricacies of two important steam turbines, which are impulse turbine and the reaction turbine. Thank you.
If you want to study this topic in detail, refer to the book by S. John Publishing. Link is provided in the description box. If you found our video interesting, please like, share and subscribe and press the bell icon for future updates.
All rights reserved. This video has been prepared for educational purposes only. No part of it may be reproduced or copied without the permission of the copyright holder.